Hey guys, Kenna here. Today we're going to be taking a look at hydroelectric and tidal energy. So let's jump right in. Essential questions. Number one, what is hydroelectric energy and how does it work? Number two, what are the advantages and disadvantages of hydropower? Number three, what is tidal power and how does it work? And four, what are the advantages and disadvantages of tidal power? So we won't just look at hydroelectric. We'll also try and give you some insight into tidal, which is kind of a developing technology now. And we'll see how much we can get out of that as well. Okay. All right. So first off, let's go ahead and take a look at what are the basics of hydropower. And this technology is using kinetic energy of flowing water going downhill to produce electricity, and it's typically known as hydropower. This is a form of renewable energy that is a resource that gets its power indirectly from solar energy because the sun evaporates the water, it condenses in clouds, rains down at higher elevations, and then runs back down to the oceans and rivers, lakes, and streams. This is part of the Earth's water cycle. Okay? And we've actually been harnessing water power for quite some time. Humans have used power of moving water for more than 2,000 years. The first reference to water mills are found in Greek, Roman, and Chinese texts, and they describe vertical water wheels in rivers and streams. These much more traditional water wheels, like what you see here, turned as the river flowed, and it turned millstones that did things like grind grain. In the 1700s, an American named Oliver Evans uh, designed a mill that combined gears, shafts, and conveyors. And after the grain was ground, it could be transported around the mill. The invention eventually led to the water wheel, which began being the main power source for sawmills, textile mills, and forges throughout the 19th century. In 1829, a French engineer, Jean Victor Poncelet, designed an even more efficient water wheel, and this was enclosed so that the water flowed through the wheel instead of around it. So this is not a new technology. This one has been here for quite some time. And we're just starting to realize that we may have tapped most of the water sources that are really effective for this. But small scale, we could still keep using hydroelectric power. And I think in the developing world, you're going to see an increase of this until we've maximized its potential. In 1880, the Grand Rapids Electric Light and Power Company used a water turbine to generate enough electricity to power 16 lights. Soon after this, in 1882, the world's first hydroelectric power plant began operation on the Fox River in Appleton, Wisconsin, as you can see here in the pictures. The plant, later named the Appleton Edison Light Company, was initiated by Appleton paper manufacturer H.F. Rogers, who had been inspired by Thomas Edison's plans for an electricity producing station in New York. And when you look at rushing waterfalls and rivers, you may not always think immediately of electricity, but hydroelectric power plants are responsible for lighting many of our homes and neighborhoods, especially here in the Pacific Northwest, as we have a higher percentage of our electricity coming from this source. So, how does it work? Water energy or these hydropower stations usually have large dams and water reservoirs. Reservoir is a store for energy, and it's possible to control the energy produced by controlling how and when the water leaves the reservoir. The process is much like turning on and off a tap of water. Okay, you can see all the key aspects here: the reservoir on the left with gate control, allowing more or less water through the dam. The penstock, which is the tube that's leading to the turbine, that then turns the turbine, which in turn activates the generator, producing the electricity that's going to go to the transformer and get stepped up into power lines. And then the water goes through the turbine. It doesn't stay there, doesn't stop, doesn't get consumed. It's not a fuel in the way we think of with coal or oil or natural gas. It comes out the other side. So you don't even necessarily have to have these big dams. All of the big projects that provide a bunch of energy do. Um, you can have a water diversion channel, and this can move water from a river and go through a little turbine and then rejoin the river later on and produce a certain amount of electricity. So what we're relying on here is the conversion from potential to kinetic energy due to gravity. So gravity causes it to fall through a penstock inside the dam, and the turbine at the end of the penstock is turned by the moving water, which spins the turbines, allowing the generator to produce electricity, and that sends it to the power lines. So you can see here on the right, these are some of the turbines that you would typically see in a hydroelectric. We have a really good example of this up on the Columbia River with the Bonneville Dam. But essentially it's a large generator, and you're using electromagnets to go ahead and circulate electrical current through the loops of wire around the stacks of magnetic steel laminations. They're called field poles and are mounted on the perimeter of the rotor. The rotor is attached to the turbine shaft and rotates when the turbine rotates as the water goes through. So this moves the electromagnet, and so in this case causes electricity to flow and voltage to be developed as it goes ahead and goes through. And we can regulate the speed of this depending on how much electricity we need to be produced. And so, excuse me, when we go ahead and start looking at this, we can turn on and turn off. That's been one of the disadvantages of things like solar, and what we'll see with wind as well, is that you've got it when it's there. But with water, because essentially the reservoir is storing it kind of like a battery, we can turn it on when we need it, turn it off when we don't. There's some benefits to having this kind of setup. Rotations can go anywhere from 50 to 600 revolutions per minute, generating our electricity. Okay. So depending on how much water you have behind the dam, that's how much energy you're going to be able to go ahead and produce by turning it on and off. And the dams can store a tremendous amount of water. And near the bottom of the dam wall is the water intake, or the sluice gates. And this is what's going to regulate the inflow, outflow. So just how much of this do we have, and what are the top producing hydropower states in the US? Well, you can see here, Oregon is number 2 behind Washington. And while Idaho is not in the top 5, it is a very high electrical producer in terms of hydropower, just based on percentage. There's just a lot fewer people, okay? Over 1/2 of total US hydroelectric capacity is generated in a few states in the Western US, mostly Washington, Oregon, and California. Washington is home to the location of the nation's largest hydroelectric facility, the Grand Coulee Dam. It's important to note that only a small percentage of all dams in the US produce electricity. Most of the dams that you see around the US are not for electric use or production. They are constructed to provide irrigation and flood control. Okay, so when you go ahead and start looking at this around the world, instead of just the United States, you can see that China, far and away, the biggest producer of electricity through hydroelectric power. South America produces a little more than half of electricity using high power. It's something like 53%. So you see Venezuela in there, not a lot. Brazil is in there. But in terms of amount of energy, they don't produce quite as much total, but a bigger percentage of their actual energy production comes from hydropower. You can see the United States comes in there at 4. We are actually behind Brazil, Canada, and China. Most electricity from water in the US and the world is produced by conventional hydropower using gravitational energy. Almost 17% of the world's electricity and 5 to 10% of US electricity, depending on the supply of water, is produced by hydropower. That's enough power to supply about 28 million households with electricity, or the equivalent of nearly 500 million barrels of oil. The total US hydropower capacity is about 95,000 megawatts. Now, another piece to kind of keep in mind here is efficiency. Just how efficient is hydropower compared to some of the other technologies that we've looked at? Well, if you think about our traditional fossil fuel power plants, especially something like, say, coal, these thermal power plants are only about 35% efficient. They don't capture as much energy as potentially there. But when we start looking at hydroelectric power, it's very efficient. We are able to capture about 95% of the moving water energy. So this is one of the biggest advantages is they've incredibly high efficiency of our hydroelectric power plants. Okay. And if we go ahead and take a look at some of the other companies, how many companies by country, you can see the US has a lot of companies, but some of them are actually not directly in the United States. When you look at average power production expense per kilowatt hour, you can see that hydroelectric is one of the cheapest. So while the initial investment in the actual building of the hydroelectric power plant is high, the actual cost per kilowatt hour is actually really low compared to, say, a gas turbine, fossil fueled steam, or nuclear power plant. And a big part of that is you don't have to pay for fuel. Okay, water's there. And so you're not having the input of fuel. It's mostly in terms of the operation and maintenance to keep it going. And because of this, we've seen a big jump in the rate of construction. But I think you notice right there in the end, after you pass the 1980s, it's starting to level off a little bit. And that's because in the industrialized Western world, we're kind of getting to a point where we've tapped out most of the places that would really be effective in terms of a hydroelectric power plant. So you're not going to see quite as much of this in the future in industrialized world. But these developing countries, I think you are still going to see the implementation of more of these dams. So what kind of things are we looking at? This is a picture of Hoover Dam, which is mostly for irrigation, because remember when we talked about when we're going over our water unit, this provides a whole bunch of water to the whole U.S. Southwest. That's a big one. This is the Three Gorges Dam, which actually produces a ton of electricity for China. It also does some flood control, but it was a huge amount of flooding. The amount of little villages and things that were actually covered by the reservoir that was produced by the dam is substantial. So when we start looking at these, there are definitely political and economic obstacles that we need to be overcome. The construction cost is huge, and you can't just put one anywhere. It is somewhat weather dependent, and it requires a backup source, okay? Because when we start looking at these different types of systems, we don't always want to use up all that water, especially if we're going to be using it for something else in terms of irrigation, drinking water, etc. You have massive displacement of people and wildlife, and water use allocations can we can have water wars over who has access to that water and for what different needs. But there are definitely some advantages before we kind of really capitalize on the disadvantages. Number one, it's renewable, okay? We can't underplay that enough. When we go ahead and start looking at this resource, rainfall renews the water in the reservoir, so it's always there. We have clean energy source in this one, right? No waste products or greenhouse gas emissions are produced. And generally, like a tap of water, it's available as needed because of reservoirs, okay? So we're dealing with something that's clean fuel source, available, right? Doesn't pollute the air like power plants that have fossil fuels, and it provides year-round water for irrigation in addition to electricity. When we start looking at this, it is a water supply for drinking and flood control, but it has a moderate to high net energy. That's pretty good. And as we saw, it's 80% plus efficient, upwards of 95% for some of these, and very low cost once put into place. And most of these dams will last 50 to 100 years, barring some sort of major earthquake or other incident. It's a domestic source of energy. We don't have to import barrels of oil from the Middle East, which makes us more independent. And just kind of a small advantage, it provides recreational opportunities in terms of fishing, boating, etc. So a pretty cool source, although it does have, as we'll see here, some impacts on wildlife. Has pretty high environmental impacts because of the displacement where the reservoir goes. There was land there before and something else lived there. It converts that land habitat into lake habitat, destroying wildlife lands, and often can drain wetlands because we are regulating water flow. It limits the amount of fresh water flowing downstream and can harm estuaries. And so while we don't have all of those fossil fuel related problems, we do definitely have environmental impacts in terms of ecosystem. This decreases fish harvest below the dam and can impact the mobility of fish and other aquatic organisms as they try and go up. We can minimize some of that with fish ladders, but it's not a perfect solution. Fish populations are probably the most at risk. If you remember when we went over dams back in our water unit, this is definitely a problem. And you have to make sure that you get them diverted around the turbines because that would kill the fish. Okay. You decrease the natural fertilizer that comes downstream. Places like Cairo, Egypt, relied heavily on the annual floods bringing nutrients down from upriver to the Nile River Delta to grow things. And with the dams being built above, there's definitely less of that beneficial natural fertilizer coming down. Reservoirs are a huge loss of water due to evaporation because they're a big standing body of water. When the water comes out of the dam, it's more turbid, meaning more turbulent, which kicks up debris from the bottom of the rivers, etc. And this can actually cause problems in terms of what species can live there and who stays close to the dam. Even above the dam, this can cause problems because you can see stagnant water increases insect populations, which can cause insect-borne diseases. So we start seeing that there are all these problems associated with it. And one of the concerns that a lot of people have, although it's incredibly rare, is that you can have a collapse of dams. Okay? Now, when you start looking at collapsing dams, there are many dams that are not maintained properly. If a collapse event occurs, you can have massive flooding and loss of life. And the average reconstruction cost for this type of thing is about $5 million, which is actually not that big. It's more the cleanup down below that ends up being really expensive. Okay, and I wanted to finish today with tidal power. It's not one of the major groups, and your book doesn't touch as much on it, but I think it's worth covering. Tidal power facilities harness the energy from the rise and fall of the tides. There are two main tidal plant facilities, what are known as tidal barrages and tidal current turbines. Ideal sites are located at very narrow channels and experience a high variation in high and low tides. And so understanding something about tides would be beneficial to you here, thinking about neap tide and spring tides and when they happen and where your greatest tidal variances are, things like the Bay of Fundy. But essentially the tidal energy is created due to the gravitational pull of the moon and the sun and the rotation of the earth. As a result of these tidal forces, water movement can be used to create electricity. The tidal electricity generation works as the tides come in and again when the tides go out. The turbines are driven by the power of the sea in both directions. Okay? And it's possible to predict tidal energy much more so than wind and solar because the tides are very predictable. This is why you can go ahead and get tide tables. Now, current plants are limited. Okay, there are some. There's a big plant in France called La France. Russia has one, Canada and China have them, and you can see the wattage production, the biggest one being that power plant in France. Okay, but there are advantages to a tidal project over some of the other things we've seen. Again, it's much more reliable. The water seems to be more reliable than wind, solar, etc. And the tidal projects are less visible than, say, a wind project or a massive dam. So aesthetically, they tend to be a little bit more pleasing because they're in the water. And this is a proven technology too. We've still had 50 plus years of use, and once installed, the costs are pretty low. On the downside, though, they can also harm fish and other wildlife just like a dam can. They don't scale very well like a wind project does. Okay, so wind projects can actually make a lot of energy pretty quickly, and you can put it up a big wind park in about a year. The designs are all over the place, some more effective than others, and so there's no consistency in the designs in terms of replacement parts and maintenance, that type of thing. Like wind and solar, tidal power is intermittent. It's when the tide's coming in, it's when the tide's going out. And so how fast that's happening, how much water is moving through, the site is very specific in these particular instances. With regards to the barrages, some of the environmental impacts of dams are also present, although to a much lower extent. And these are very, very, very expensive to install because it's out in the ocean. And they're not as efficient. Unlike the dams that we just looked at before and other hydropower systems, tidal systems only produce about 1/3 of the electricity that hydropower plant can of equal size. So there's much lower energy output. And because they're so difficult to install, they're also really difficult to maintain. But there are some current projects out there. In August, CGen built a 1.2 megawatt dual turbine unit that is connected to the power grid outside of New York's East River. They also have a 2.25 megawatt turbine in Portugal. So that's just one example. You can see kind of the design there. Efforts are underway to anchor turbines to the ocean floor to harness tidal energy. And while concept is proven and in practice, a handful of locations have been identified on a small scale, you don't see major electric production here yet. This form of generation has many advantages over other tidal energies, and the turbines are completely submerged and therefore out of sight. They then don't pose a problem for navigation of shipping because they're so deep, and they don't pose a problem in terms of, the aesthetics. They require use of much less material and construction, but they are in a difficult place to go ahead and build. Tidal turbines are vastly better than wind turbines in terms of efficiency. A tidal turbine produces 4 times the output power per square meter of sweep area as a wind turbine, with a substantially smaller environmental impact. And here's another one. This is the Siemens CGen's tidal turbine. You can see the actual final, not just a drawing, but the actual device itself. So there's some potential here as well. Okay, guys, that's what I've got for you. Stay healthy, stay safe, and I'll see you soon. Take care. Bye-bye.